So G will be a group under the binary operation star if it satisfies the following four conditions. One is that it's closed. You have a closure property. So A star B will always be in G. For any pair of elements you pick in G, A star B will always be in G. So the next thing is associativity. So you can put your brackets anywhere. If you put your brackets here, there's no problem if you put your brackets here as well. So this is the associative property. And this does not matter. Any three that you pick from the group, it will satisfy this associative property. A star B star C with the brackets on B and C is the same as A star B star C with the brackets on A and B. So the next property is that there must be an element in the set such that this element, we call it E, and A star E will be equal to A to be equal to E star A for all elements in A in the group. So it doesn't matter which element A you pick. Any element A you pick in the group will satisfy this property. It will remain unchanged under this operation. A star E will be equal to A. And this identity element will work on both the right and also on the left. It doesn't matter which side you multiply it, it still leaves the element of the group unchanged. So this element E, we shall use this symbol E to represent such an element, and it's usually called the identity of the group. So some books will use this symbol 1 to denote the identity. So as you read other books, you may find they use a symbol 1 to denote the identity. That should not confuse you. Now, the next thing is for any element in the set G, there exists another element which is also in the set G. It must be in the set G. And we denote this element by A with this -1 as the exponent. We read this as A inverse. So there must exist another element in the set such that A star A inverse will be equal to the identity element. And even if you change the order so that you have A inverse star A, you still get the identity element. So this element A inverse is called the inverse of the element A. So many times when students are talking about the inverse, they say that some usually wrongly state that the group does not have an inverse. That is wrong. Every element has its own inverse. So you cannot say that the group has an inverse or does not have an inverse. The group does not have an inverse. It's each element that has an inverse. So take note of that. Oh, there are some parts of this slide which are missing. The set, the elements of the set must be very clear in your mind. And secondly, you cannot have more than one binary operation for a given group. So the same set can be a group, you can have different binary operations on the same set, but you can only consider one at a time. So you can't consider two binary operations or more in one go. So anytime you're talking of a group, it's just one set and one binary operation, no more. Also, the number of elements in a group is called the order of a group, and we shall denote it by this symbol where you put the two straight lines on the side of G. So a group is said to be finite if it has a finite number of elements. So the number of elements in G is finite. Otherwise, we say that a group is infinite. I think there are some people trying to join. I will admit them, then we proceed. You should try to join early so that they don't interrupt the class. So here are some remarks. So anytime you want to check if a set along with a binary operation is a group, it is necessary that all the 4 properties are satisfied. So if any one of them is not satisfied, then the set fails to be a group under the given binary operation. So if you want to check that a set is a group or it fails to be a group, you just need to find one operation which does not work. So once you find one operation which does, or rather one property which does not work, then you're done. You don't need to check the others because it will be pointless. For it to be a group, all the 4 properties must be satisfied. So anytime you find one that does not work, one that is not satisfied, then you simply stop there and conclude that the set will not be a group under the given binary operation. So basically what I'm saying is that if you are showing that a set is not a group under a given binary operation, you simply need to find one operation, one property among the 4 that we listed earlier that are not satisfied. One property that is not satisfied. So for the sake of convenience, many times we will ignore this symbol for the binary operation. So instead of writing A star B, we shall just write this as AB for brevity. So this notation AB is what we call the multiplicative notation. So you can write a binary operation multiplicatively by I think, juxtaposing, putting them side by side without anything in between and no space. So many times when there is no ambiguity about the binary operation, we shall just denote this A star B as AB. So sometimes instead of writing AB, we can denote the operation by A plus B. So sometimes this is convenient to denote the binary operation as A plus B. And this is what we call the additive notation. Sometimes this is convenient, and sometimes this will be convenient. Most of the time, we shall use this multiplicative notation for most of the work we are going to do. So where necessary, there might be situations where it's necessary to use the additive notation, and that's what we'll use. So this one we already stated earlier. This symbol, this element A inverse is called the inverse of A. And if the binary operation is written additively, so the inverse will no longer be denoted by this A inverse, it will be denoted by minus A. So when you choose to write the binary operation additively, the inverse will now be denoted by negative A. So if you have a finite group, if the number of elements in the group is finite and it's a small number of elements that you can draw and fit in your book, then you can usually represent them as a table, multiplication table. Or some books will call it the group table. And there's also another name for it, the Cayley table. So you will have to let me know if you can hear me. Sometimes the network disappears and I'm not aware.
We can hear.
Okay. Let me know if at one point the voice disappears, let me know. I think there are some people still trying to join. I will admit them, then we can proceed. So I think these remarks are clear, and you will have a chance to read them again. So we now consider some examples of groups. So one example is a set of real numbers, which we represent with this symbol, this fancy looking R. And the binary operation we consider is addition of real numbers, the usual addition of real numbers. So under usual addition of real numbers, if you add any two real numbers, you will also get another real number. This is something you know. So the closure property is satisfied. This is also another property you are familiar with. Addition of real numbers is associative. You can put your brackets either the second pair or the first pair, and you still get the same answer. So the next thing is we know there's an element 0 in R. The number 0 itself acts like the identity. So A plus 0 leaves A intact, and it works on both the left and the right. So the identity element in this group is 0. 0 is the identity element because when you add 0 to any real number, you get the same number. So the negative of the real number, if added to the same number, will always give you 0. I think this, again, you know from your knowledge of real numbers. So A plus negative A will always give you the identity 0, and it works on both the left and the right. So negative A plus A is the same as A plus negative A, and both give you the identity 0. So this negative is the inverse of A. So for instance, if I have a number like a half, negative a half will be the inverse of a half. Are we together?
Yes, sir.
So this should be...
Yes, yes.
Okay. Should I move faster?
No?
The
Okay.
pace is okay.
Okay. So again, we can consider the set of integers under addition. Again, the properties are all the four properties will be satisfied. If you add any two integers, you get another integer. So closure, the property of closure is satisfied. Addition of integers, because the integers are just real numbers, so they won't behave any differently. So addition of integers will also be associative. For any three integers you pick, this property will be satisfied. So number 2 is satisfied. Number 3, 0 is an integer, and it will serve as the identity in the group because any integer plus 0 gives you the same integer. So again, 0 is the identity element in this group. And the negative of the integer will act as the inverse. So A plus minus A will always give you 0. This is minus A plus A for all A in Z. So negative A is just the inverse of A. And here the binary operation is written additively. So the inverse is written as the negative of the element. So here is a question. Is a set of integers a group under multiplication? Does anyone have an answer to this? Anyone?
I think it does not form a group under multiplication because some elements might lack the inverse under multiplication.
Yes, that's correct. So I will then let's look at the solution. A set of integers will not be a group because, as you said, some elements, in particular, for example, 0 will not have an inverse, and many other elements will not have an inverse. For instance, 2 will not have an inverse. The reason for that is the inverse must be an element in the set. We know that the identity, what will behave like all the other three properties will be satisfied. So if you start from the first property of multiplication, you multiply two integers, you will get another integer. Multiplication of integers is associative, and 1 acts as an identity element in this set. But now we have a problem with the last property because some elements will not have inverses. Because, for instance, I cannot find another integer which, if multiplied by 2, will give me the identity, which is 1. So if I'm looking for the inverse, I must look for an element that is in the set. And if I pick 2, I cannot find another element in the set, which when multiplied by 2 will give me 1. So 2 does not have an inverse in the set. The same with 0, the same with a half. So this one fails to be a group under multiplication. The reason for that is that some elements, actually most elements, will not have an inverse. So, but there are some exceptions. There are two integers, namely 1 and -1. These ones will have inverses. So if I pick only these two and form a set with only those two, then I can create a group with only two elements, that is 1 and -1. So this will still satisfy all the 4 properties and will also satisfy the will satisfy all the 4 properties now, because we have eliminated all the elements which don't have inverses, and we are left with only the ones that have inverses. So I can set up this set, 1 and -1, and it's actually a group under multiplication. Usually we denote this by Z star, Z with a superscript star up here. It has only 2 elements, 1 and -1. So in your own time, you need to convince yourself that all the 4 properties are satisfied. All the 4 properties for a group are satisfied. So again, here is another question. Is a set of real numbers a group under multiplication? Anyone with an answer? I think let me admit some more people as you think about the answer. Anyone with the answer? Who can tell us if a set of real numbers is a group under the usual multiplication of real numbers?
Excuse me, sir.
Yes, you're excused.
I think it is not can't be a group under multiplication, since any real number multiplied by 0 will remain to be 0. It won't be real again.
0 is a real number. Zero is a real number. I don't know why you assume that 0 is not a real number. So I see Francis has raised his hand. Francis, what you'll do in this class, if you have a question to ask, please just put on your mic and speak. Don't raise your hand. Because most of the time I'm looking at the slide, I'm not able to follow. The slide covers the whole screen, so I can't see what is going on the Google Meet side.
Oh, okay.
Yeah.
I wanted to say, I don't think 0 has an inverse.
Yeah, it definitely does not have an inverse. So that is your reason for.
So I'd say it's not a group under multiplication.
Correct. So you observe that all these three properties are satisfied. So this may make you think that it is a group. And then if you check, all non-zero elements will have an inverse, because the inverse of A will just be the reciprocal of A, right? But we have a problem with 0. 0 has no inverse. From the definition of a group, there should be no exception if all elements must have inverses for it to be a group. So if you find just one element which has no inverse, it fails to be a group, right? So all elements must have inverses for it to be a group. But here we have a problem because there's one element, 0, which does not have an inverse, because I cannot find another integer, sorry, I cannot find another real number to multiply by 0 to get my identity element, which is 1. And therefore, it fails to be a group. But all is not lost, because we can we can still do some work. So the conclusion is that it's not a group under multiplication. So since 0 is the only element that has no inverse, we can remove it, and the remaining numbers will now be compliant. So once we remove 0, we end up with all the non-zero real numbers, and now all of them now will have inverses, and that makes this set a group under multiplication. We denote these non-zero real numbers by R star, superscript star. So anywhere you see R star, we mean the non-zero real numbers. So here is another example. We have a set of all n by n invertible real matrices. Real matrices simply means the entries in the matrix, in the matrices are real numbers. So the challenge is to prove that G is a group under the usual matrix multiplication. So you have to remember that we are not considering all n by n matrices. You're only considering the invertible n by n matrices. So it's not the whole set. It has to be clear in your mind. Your definition of the set must be very precise, at least precise in your mind. And the binary operation here is clearly matrix multiplication. So let's see. We need to check that we need to check that it is closed. So if you pick any two elements, two matrices in this case, if you pick any two matrices A and B in the set, then their product will also be in the set. But what do you need to satisfy to be in the set? It means it must be an invertible matrix. So we need to be sure that if you multiply two invertible matrices, we should get another invertible matrix. So we simply check, does this product have an inverse? Is it invertible? And it is, because if you try to get the inverse of the product, you actually get it as A inverse multiplied by B inverse. Now, A inverse and B inverse already exist because they have been picked from the set, and the set consists of invertible matrices. So the inverse of A and B will both exist. So this proves that if you multiply any two invertible matrices, you will also get an invertible matrix. And that proves the closure part. So this one, matrix multiplication, is associative. This can be proved, but we will take it for granted because you have done this before in linear algebra. So that should not be new to you. But there's a proof for this as well. If you want, you can look it up. So the n by n identity matrix will act as the identity of the identity element, because if you multiply any matrix by the identity matrix, you leave it intact. So now the important thing is that we need to confirm that this identity element is also in the set. So yes, it is, because it is invertible. The inverse exists. The inverse of the identity matrix is just the identity matrix. And therefore, it means the identity matrix is in G, because it is invertible. Now, again, by definition, these matrices are supposed to be invertible, so their inverses will exist, and just the inverse of the matrix will act as the inverse. The usual inverse of the matrix will act as the inverse. So now the other thing we need to be sure of is that the inverse is also in the set. So you need to get the inverse of the inverse. So the inverse of the inverse turns out to be A itself. This, again, you should know from your linear algebra, which is in the set G. So the inverse is also invertible. And therefore, we can conclude that this is a group under the usual matrix multiplication. It has a special name, and it's normally called the general linear group of degree n. N is determined by the size of the matrix. And we write it as GL, and then in brackets n, comma, the real numbers. So this R simply means our the matrices, the entries in the matrices are real numbers. And n here simply means they are n by n matrices. So this is called the general linear group of degree n. And it contains only the invertible matrices, no other type of matrices, only the invertible ones. Any questions on this? I think there are some people still trying to join. I will go back and admit them. No, I don't see any. So also, for now, I may not be able to respond to comments until the end of the class. So you can type in your comment, but I will not be able to respond to it until the end of the class. So here is another example. We have the set K, which consists of all invertible matrices. Remember, this general linear group consists of invertible matrices, but we want to limit ourselves to just those that have determinant 1. So again, this is just a subset of this general linear group. And that limits us to only the determinant, the matrices that have determinant 1. So the task here is to check that K is a group under matrix multiplication. So we need to go through all the 4 properties. Now, again, remember, this must be very clear in your mind. The elements that we are working with are just the matrices whose determinant is 1. So any other matrix with a different determinant is kicked out, and they have to be n by n matrices. Remember, the general linear group consists of only the n by n invertible matrices, and we consider a smaller set just a set with determinant 1. So we prove that K is a group under matrix multiplication. We pick any two matrices in K, and since they are from K, they will both have determinant 1. So the determinant of the product AB will, this again from your linear algebra, you know this is true, that determinant of AB is the same as the determinant of A multiplied by the determinant of B. And since each of them is 1, to just be 1 times 1 to give us 1 again. So we have shown that the determinant of the product of A and B is also 1. So if I multiply two matrices in K, I will still get another matrix in K because the product still satisfies the required property. It has determinant 1. So the next thing again is simply inherited. You are familiar with the fact that matrix multiplication is associative. Again, we'll just take this as true. This is well known because we assume you have done this in linear algebra. But like I said, this is something that you should be able to prove. You can go back to the linear algebra and look up the proof. So the next thing is to find out if we have an identity in the set. And the identity matrix also turns out to be in the set because it has determinant 1. And you know that if you multiply any matrix by the identity, it remains unchanged. It's left intact. So the identity element turns out to be in the set. The identity matrix, rather, turns out to be in the set, and it will serve as the identity element. So last but not least, the fourth property is again, remember these are all invertible matrices. So all we need to confirm is that if A is a matrix in this set, will the inverse also be in the set? So to check if the inverse is in the set, we need to confirm that the determinant of the inverse will also be equal to 1. So if A is picked from K, we already know that since it's from K, the determinant is equal to 1. And we know that the determinant of the inverse of A is obtained by this formula, 1 over determinant of A. You also should know this from your linear algebra. But we know the determinant of A is 1, so this is just the same as 1 over 1, and it's equal to 1. So we have confirmed that the determinant of the inverse is equal to 1, and therefore the inverse of A will also be in the set K. And of course, anytime you multiply A by its inverse, you will get the identity. The same if you multiply A inverse by A. The order will not matter. Hence, all the elements of K are invertible. And therefore, we can conclude that K is a group under matrix multiplication. So this group has a special name also. It's called a special linear group. So it's a subset of the general linear group, which is also a group on its own. The set of matrices that have determinant 1. So it's called a special linear group, and it's denoted by, we shall denote it using this. Some books may vary this notation slightly, but we shall work with this for our case. Any questions on this? I think let's check if there are any people trying to join. So are there any questions on this? So you notice that you will be required to recall some of your knowledge from linear algebra so that you can use it here. It may be a good idea to review your notes on linear algebra, because anytime we work with matrices, we shall be using the properties you learned. So we now look at another, probably this is the last example we shall look at for today. We now look at the symmetries of an equilateral triangle. So basically, we are considering transformations of an equilateral triangle which leave it unchanged visually. In other words, if there are no labels at all on the triangle, you would not notice that it has moved. So there are a total of 6 such transformations, and we can obtain them by simply keeping track of the effect of the transformation on the vertices. That is enough. If you keep track of where the vertices go, that is sufficient to determine each of the transformations. And eventually we shall represent them as bijective functions. Later on we shall study permutations, and we shall cover this in a little more detail. So I hope you get this right. Basically, it means if you have an equilateral triangle on your table, and someone performed a transformation on it, it will only be a symmetry if you don't notice that it has moved. So the assumption here is that there is no labels. There are no labels at all on it's plain completely, and therefore you're looking for the transformations which would guarantee that you will not notice that it has moved if it was on your table. You may have covered some of these in SMA305, so it's just a good reminder. So the first transformation we look at is what we call the identity transformation. So initially we shall start with this as the triangle, the top vertex labeled 1, and moving anti-clockwise we have 2, and then 3. Second one is labeled 2, the third one is labeled 3. So all the transformations are going to be done on this triangle. So the identity transformations means you do nothing to the triangle. So every single point remains exactly where it was initially. So again, it looks exactly the same as the initial triangle. So you will not notice that it has moved if you do nothing. The other thing you can do here is rotate it about the center through 360 degrees. It goes back to the same point. But let's just assume you do nothing to the triangle, so it doesn't move. So that is one of the symmetries. So if you're going to represent this as a function, this is what we have. The 1 does not move, it remains exactly where it was. So 1 goes to 1, 2 does not move, it stays exactly where it was. 3 does not move, it stays exactly where it was. And this is how we represent it as a function. The function itself takes this name E. So we say E is a function, and the value of E at 1 is equal to 1, the value of E at 2 is 2, and the value of E at 3 is 3. So this gives us a representation of this transformation as a bijection. Bijection simply means one-to-one and on-to function. We shall see this when we cover permutations later. For now, this should be sufficient. Are there any questions on this? So this transformation can now be represented as a function like this. Okay. So we will look for other transformations that have the same effect, where if there were no labels, we would not notice that the triangle has moved. So what the other transformation that also works is a 120-degree rotation about the center, and we call it A. So this transformation A rotates this triangle about the center. Center simply means a point where the center of mass, but for us we just call it the center. It's a point where the altitudes will meet, or the bisectors of the angles will meet. It turns out to be, it's a center. So you rotate it about the center anti-clockwise through 120 degrees or 2 pi over 3 radians. Then this is what happens. One, if you take it through 120 degrees, 1 will move to where 2 is. So we have 1 will go to 2. So you can see 1 has moved to where 2 was. What will happen to 2? 2 will move to where 3 is. And there it is. So 2 goes to 3. And 3 will move to where 1 was. So 3 now takes the place of 1. So 3 goes to 1. So again, as a function, you can write it as a of 1 is 2, a of 2 is 3, and a of 3 is 1. If you notice any error, you let me know. Sometimes I may not, the diagram and the function may not agree if I made an error. So keep your eyes open for any errors. So this gives us a second symmetry. Again, you notice that if there are no labels, you would not notice that this triangle has moved at all, but we have rotated it. So the next transformation we'll consider again is a rotation through 240 degrees. So this is 120 degrees 2 times. So it means if you do that twice, again, you rotate it about the center. Since there will be 2 rotations, 1 will move all the way to 3. So 1 takes the place of 3 here in the new setup. 2 will go to 1 because if you go through 240 degrees, it means you will turn all the way and 2 will land here at 1. So 2 goes where 1 was and 3 goes where 2 is. So we denote this function by a squared. And we see that a squared of 1 is 3, a squared of 2 is 1, and a squared of 3 is 2. So as a function, this is what it will look like. I will just admit a few more people, then we can continue. So this gives us the second transformation. Again, now it is just a function. No, sorry, it's a third, I think. We had the identity, we had the 120 degree rotation, and now we have the 240 degrees rotation, or 4 pi over 3 radians. The rotation here is positive, so you can see this arrow shows you're going anti-clockwise. A positive angle is usually taken to be a positive rotation is supposed to be anti-clockwise. So there you are. You have the third symmetry. So any other rotation, for instance, if you take the 360 degree rotation, that one will simply take you back to the original state. So it behaves like the identity. So we will not look at the 360 degree rotation because it simply behaves like the identity. It's the same as the identity actually. So we'll be repeating. So that gives us all the possible rotations that are different from the identity. So now we consider the reflections. The first reflection will be along the altitude that goes through this vertex 1. So this will simply, since this acts as a mirror line, that means anything that is on the mirror line does not move. So 1 remains unmoved, but 2 and 3 will be switched. So 1 stays at 1, 2 goes to 3, and 3 goes to 2. We call this function B. Are we together?
Yes.
Together.
Yes. So the next one again is we use a reflection, but through the altitude that goes through the vertex 2. This line through the vertex 2 is our mirror line. So since 2 is on the mirror line, it doesn't move. 2 remains fixed, but 3 goes to 1 and 1 goes to 3. So 1 will go to 3 and 3 will go to 1. So we call this function C. I think by now you have gotten the hang of it. I don't need to explain too much. So the next one we have is now final reflection through this line, that the altitude that goes through the vertex labeled 3. So again, 3 will be on the mirror line, so 3 does not move, but 1 and 2 are interchanged. And this is what we get. As a function, this is how it will look. 1 will go to 2, 2 will go to 3. This is a, there's a problem here. One should go to 2 and 2 should go to 1. 3 remains fixed. 3 will go to 3. I can fix this before we continue. I don't think it will be, or maybe you can just note that in the actual slides that I will share, I will fix that before I share. So maybe it's a good idea to note that there's a problem here, because what it says here is it's supposed to leave the vertex 3 fixed, but interchange 1 and 2. So 1 and 2 should be interchanged, but 3 does not move. So note that here 3 will go to 3, 1 will go to 2, and 2 will go to 1. So what we're going to have here is 1. Sorry, we'll have 2 here. We should have 1 here, and we should have 3 here. So just note that down in your book. But I will fix this before I share. I'll just note it down. So now we have 6 different transformations, which we call the symmetries of an equilateral triangle. There are no other transformations which will leave the triangle appear unmoved visually. Those are the only ones. So we gave them names, each of the transformations, and we treat them as functions. So we have E, A squared, B, C, and D as our functions. And we shall denote the set containing these functions as D3. D3 contains E, A, all these 6 functions. Since we already know what they are, we can just write them by their the letters that represent the functions. So since they are functions, we can do some operations on functions. So operations on functions, one of them is, one operation that you can do is a composition of functions. So we take composition of functions as our binary operation. And it turns out that when we do that, this set will be a group. And it also has a special name. It's called the dihedral group of degree 3. So we in the next slides, we are going to see how we perform this composition of functions on this set, D3. So for now, you will have to believe that it's a group, but we shall see why in a minute. So we first of all get the composition of A and the identity. So remember how composition is defined is that the function on the right is the one that acts first, and then the function on the left follows. So the domain, of course, is just the vertices of our equilateral triangle. So the identity will act first. The identity does not change anything, so everything is left intact. And then this function A will act second. The function A sends 1 to 2, sends 2 to 3, and sends 3 to 1. So finally, this composition will send 1 to 2, and it will send 2 to 3, and 3 to 1. So we show that in the next bullet here. So here we see the composition itself in full. So A of E is actually the same as A, because if you go back and check the function A, this is what it looks like. 1 will go to 2, 2 will go to 3, and 3 will go to 1, which is exactly A. So A of E is just the same as A. Doesn't change. So you can check with all the other functions in your own time that any of the function composed with E leaves the function intact. That is true for B, C, D, as well as A squared. So basically, what this says is that this element, this function E, behaves like the identity in our set. So we can try one more. Let's get A of B. So again, remember when you're getting the composition of functions, the function on the inside acts first, followed by the one on the outside. So B will act first. Remember, B is a reflection, right? Which leaves 1 fixed and interchanges 2 and 3. So B will take 1 to 1, will take 2 to 3, and will take 3 to 2. Then A will act after that. Remember, A takes 1 to 2, it takes 2 to 3, and it takes 3 to 1. So when you compose A and B, what will happen is that 1 will eventually be taken to 2, 2 will go to 1, and 3 will go to 3. And now the composition is illustrated here. It's shown here. So the composition of A and B turns out to be D. Remember, D is a reflection to the altitude that passes through the vertex 3, which leaves 3 fixed and switches 2 and 1. So when you compose A and B, you will get D. So I can give you an opportunity. Can you work out B of A? You can do this in your own time. So we can put all this information in a table, the composition. We can set up a group table for this. So for instance, the one we have done is what? It was A of B. A of B is here. You will get D. If you compose A and B, you get D. So how it works, this here is going to show you how this works. So any entry in this will mean the composition of what is in the first column and what is in the first row. So this is B of B. So for instance, what will go here will be the composition of C and A. So it will be C and A squared. So here you will have C of A squared. So you should not leave your, can you please put off your microphone? There's someone whose microphone is on. I don't know who is this. Who is, let's find him. someone whose microphone is on, but I can't see. Yeah. It's Wambua. Wambua, wewe ndio unapiga kelele bwana. So I've muted that one. Let's continue. So this is how you fill up the table. Any entry will pick, the order will be, you pick what is in the column and compose it with what is in the row, the first row. That's how it works. So I've filled some of them. You can try to fill all of them. But what you notice is that if you get a composition of any two of them, you will get the result will be one of the elements in the set D3, one of the functions. So it's closed. The closure property is satisfied. This is a finite set, so it's easy to check that it is the closure property is satisfied. So any of those compositions will give you another function within the same set. So it is closed. Also, when you work it out, you will see that if you compose A with A squared, so if you compose A with A squared, you get the identity. So it means the inverse of A is just this A squared, right? The B composed with itself will give you the identity. This is because the reflection, if you reflect it again, you simply go back to the original triangle. So B composed with B itself gives the identity. So that the inverse of B is just B. All the reflections are their own inverses. So C inverse is just C, and D inverse is just D. So every element has an inverse within the same set. And therefore, and one more thing which now should be just from your knowledge of functions is that composition of functions is associative. In this case, it is associative. So all the four properties will be satisfied, and this will form a group under composition of functions. So this is the dihedral group of degree 3. So in your own time, you need to fill in these blanks and complete. I've done most of them, so you only have a little to do. So D of B, you need to work it out completely and write it as one of the elements in the set. The reason this one is here is to guide you on how to, the order of the operation. The order simply starts from the column here, followed by the row. So D of B. So you can do that in your own time and fill them up. Now there's an observation we can make which will help us out. So the following is true. We observe that C is the same as A squared composed with B, and D is the same as A composed with B. So I can write everything in terms of A and B as follows. And then also, just to make our work easier, we write this composition of A and B. This A of B, we simply write it as AB. That's just for convenience. But anytime you see AB, you should remember that it is a composition of A and B. And the order of the composition is from right to left. B acts first, followed by A. So with these two ideas in mind, we can now write all the elements in the dihedral group as follows. We have E, A, and A squared. A squared is just a composition of A with itself. So A squared can be written in terms of A. Then we have B, and AB is the same as D, and A squared B is the same as C. So we can write all the elements of D3 in that form. So once you have one rotation, this 120 degrees rotation, and you have the one of the reflections, you can write all the other elements in terms of that rotation and the reflection. So this is another way of writing the elements, and a useful way of writing them, as we shall see later. So another thing we shall observe is that A cubed will give you the identity. A cubed will simply means A composed with itself 3 times. That is, you do the 120 degree rotation 3 times, which means you'll have done 360 degrees rotation, and that takes you back to the original triangle, which is the identity. So A raised to 3 will be the identity. Now BAB is the same as CB. That is, BA is actually equal to C. You can check this from the table. And CB is the same as A squared. So we can choose to write this as, if you multiply, since B is its own inverse, we can multiply both sides by B inverse here and B inverse here. B inverse is the same as B, so you can just write it as B. So if you multiply both sides by B, you can end up with this BA is equal to A squared B. So that's one other useful relation. So now you can also write this as B inverse AB is equal to A inverse. Now remember, this is the same as, it's the same as what we have here. BAB is equal to A squared, because the inverse of A is just A squared, and the inverse of B is just B itself. B was the reflection. So all these are very useful relations, and then you can use them to simplify the computations. So when you're doing the multiplication using this setup here, this notation, you will use these operations in here to convert any of the products into one of the elements in this set. So I will do an example to illustrate this. So suppose I'm getting B, and I'm composing that with this A squared B. So using associativity, I can put my brackets anywhere, and I know that A squared is the same as A composed with A. And I know that BA, using this relation here, BA is equal to A squared B. So I can replace BA with A squared B. And now using the property of associativity, I can shift my brackets here. And I know BAB, which is here, BAB is the same as A squared. I can replace this with A squared. Using associativity, I can write out this as A composed with itself 4 times, and then I shift my brackets to the last 3. So I can write this as A3, which is the same as, we know that A raised to 3 is the identity, or rather A composed with itself 3 times is the identity. So I can replace this with the identity, and then I have AE is equal to A. So I have shown that if I get the composition of B and A squared B, my answer will be A. So B and A squared B gives me A. So using the same properties, these relations that you have set up here, we can get all the products of each of the elements here and write everything in terms of A and B. So these relationships here are normally called the defining relations of a group, and later on we shall work on this in a more formal setting. But this will be sufficient for now. So the next thing we want to do is symmetries of a square. But I propose that we stop there, unless there are any questions. Then we will start on the symmetries of a square next time. Symmetries of a square will follow the similar pattern or similar ideas. But the only difference is now, instead of having 3 vertices, we'll have 4 vertices to deal with. You can still hear me?
Yes, we're getting you.
Yes.
Yes, we are.
Any questions?
Excuse me, sir.
Yes.
There are some students who are doing applied mathematics, and they have our class. This is SMA. That is SMA 303, only in the afternoon and Friday. So they were suggesting if you can fix this class to be held on either Tuesday or Wednesday, because there's a
They are doing what? Okay,
SMA,
we will solve
SMA 303.
For the time being. Can we first have questions on the content, then we'll deal with the timetable issues. Are there any questions on the content? Yes.
I have a question. How is it possible that the inverse of reflection is just the same? Like, for example, the inverse of B is B.
Yes. If you compose B with itself, you will get the identity. Try that on your own. So compose the function B with itself, you will get the identity. So that means B is its own inverse. It's similar to, if you look at the group, I'll take you back. A similar case will appear here. Consider this set. Can you see the screen?
Yes.
So this, we agreed that this will be a group under multiplication with only these 2 elements. So now the identity element in this case will be 1, right?
Yes.
So the next element is -1. Now what will be the inverse of -1? If you multiply -1 by itself, you will get
1.
1. So the inverse of -1 here is -1. So you can see here is an example where an element is its own inverse. So if you go back to the reflection, if you look at the diagram yourself, so suppose if you do the reflection, what happens? 2 and 3 are switched. Now, if you do the reflection again along the same line, what happens? 3 goes back to where it was, 2 goes back to where it was. So you go back to the identity. And how do we define the inverse? The inverse is where the operation B composed with some other element will give you the identity. Here it turns out that B composed with B gives the identity. So that simply means you repeat the reflection. After you've done the reflection, repeat it again here. What will happen? It will go back to the identity. Is your question answered?
Yes, yes. Thank you.
Okay. Any other question on the content? Any other question? So I think we can stop the recording there. If you have any questions, You can ask. So I think that will bring us to the end of the class, and we'll meet again tomorrow.